Hello there and welcome. This video is on section 5.1 through 5.3. Just go back a little bit of history here. In chapters 2 and 3, we talked about data sets and how the data was distributed. And math people have discovered three main characteristics or ways to measure a data set to understand it. The three ways are: what is the center of the data? What is the variability, the spread out of the data? And what is the shape of the data? So we call this a distribution of data, and we measure the center, the spread, and we also the shape. So in chapter 4, we talked about probabilities of things, right? We learned lots of ways of calculating probabilities of different events, permutations and combinations and other things like that. So chapter 5 is a marriage of those two things. So we're going to be looking at a distribution of probabilities. And that sounds a little confusing at first, but trust me, after this video, you'll have a much better idea of what we're talking about here. I'll go over through the main learning objectives. So the first main learning objective is to explain the characteristics of a discrete probability distribution. And then once we do that, we're going to be using some formulas for the mean and standard deviation of a discrete probability distribution. And then we're going to be doing the same kind of thing with a binomial probability distribution. And we're going to be doing formulas for the binomial probability distribution, the mean and standard deviation of the binomial probability distribution. And we also have an additional formula to find the probabilities for n observations. We have two more different types of probability distributions: geometric probability distribution along with its formulas, and the Poisson probability distribution and its formulas. So there's four types of probability distributions we're doing in chapter 5. One of them is way more important than the other ones, and that's the binomial probability distribution, right? It is overshadows the other three of them by quite a bit. So if you're only going to have to learn one of these, I think you need to learn all four of them. But if you're going to focus on one of them, let that focus be on the binomial probability distribution, because it is the one that is used most often, and you'll have the most kinds of problems associated with binomial probability distribution. Okay, so let's get to the explaining what all this stuff is and how to use the formulas. Okay, so the first objective here is to explain the characteristics of a discrete probability distribution. And there's a lot of words there. I know for this particular learning objective, I'm going to start with an example because I think it's much easier to understand all the words when we have an example in front of us. So here's my example. I just chose little numbers just to make it easier to explain. So what I chose was a multiple choice quiz where there are only three questions, right? So the three questions, each question has four possible choices. There's only one of the answers. One of those four possible choices is correct. I guess I didn't say that specifically, but I think that's an assumption. And I have shown over here a probability distribution when guessing at all three answers. So there are three questions. So if you're guessing at all three questions, you could get zero questions correct. You get one question correct, two questions correct, or all three questions correct. So there are four possible, number of correct answers that you can get: zero, one, two, or three. For each of those things, there's a probability. If you're just guessing, in order to get zero answers correct, that means you have to be wrong on the first one, wrong on the second one, wrong on the third one. To be wrong, since there's only one choice out of four that's correct, to be wrong is a 3/4 chance of being wrong, which is 75%. Same probability, 75% for the second one to be wrong, and again 75% for the third one to be wrong. So if you multiply 75%, 75% together, you end up around 42%. So if you get the probability that you get zero answers correct by just guessing is 42%. And if you end up getting one answer correct, you're just guessing and you get one answer correct, we can do the probability, and it's also 42%, which is sometimes surprising to students because they think it should be higher or lower. To get one answer correct, you'd have to get 1 out of 4, 25% on one of the questions, and then the other two have to be wrong. So those have to be 75%, 75%. But there are 3 different permutations of where you can get that one answer wrong. You can get the one answer wrong on the first question, or on the middle question, or on the last question. I'll show you some quick calculations on Desmos. So up here, the top line, I just typed all the stuff in to save time for the video. To get 3 wrong answers means 0 correct answers. So to get 0 correct answers, the first one has to be wrong 75%, 75%, 75%, which ends up being around 42%. To get exactly 1 correct, you'd have to do it a 25%, which is 1 out of 4. That's your chance of getting it right. And the other 2 have to be wrong, which we know is 75%. But we have to do a permutation of where the wrong answer is. And that's a permutation of size 3. We're choosing 1 from 3. So it's P3, 1. So you do 3 factorial or 3 minus 1 factorial. And you see it ends up being the same 42%. And we can do more of these calculations. I don't want to focus on chapter 4 stuff. I want to focus on 5 stuff. So, oops, that's for later. If we get 2 questions correct, the probability turns out to be 14%, and 3 turns out to be 2%. So we have all these different possible number of correct answers, and for each of those, we have a probability for that particular thing. And this is kind of what we mean by a probability distribution, specifically a discrete probability distribution. So now I'm going to say what all these words mean. Okay, so it has to be a variable x. The variable in this case is the number of correct answers. So the number of correct answers could be 0 or 1 or 2 or 3. When we have a thing that we're measuring, which is the number of correct answers, math people call this a variable. They like to use a letter to represent the variable, and they're very boring. They like to use the letter X predominantly to represent the thing we're measuring, which in this case is the number of correct answers. That variable X has to be quantitative, which means it has to use numbers. It has to be discrete, which means it has to be like specific numbers. Right? It can't be like ranges of numbers or weird, like, you can't have 1/7 and, all kinds of weird stuff. You're getting 0 or 1 or 2 or 3. There's 4 specific discrete possible values for X. So to have a discrete probability distribution, first thing we need is a variable X that is both quantitative and discrete. There's more. The next thing is that for each of those values of X, each of the possible correct answers, we have a known probability Px. And that's what I was describing before. For 0, if you got 0 answers correct, there's a 42% chance that will occur, and so on and so on, right? So each of these outcomes for X, each of these possible values of X has an associated probability for it. And so that's also necessary. And the other stuff about probabilities is, as we've discussed and understood before, if you have a probability of 0, that means something will never happen. So Px equals 0 means X will never happen. Px equals 1 means it'll always happen. All the probabilities have to be between 0% and 100%. And if you add all the probabilities together, they have to equal 100%. You could take these numbers, 42%, 42%, 14%, and 2%, add them together, and you get 2, 4, 8, 10, carry the 1, 1, 0, and 1. So you get 1.00 or 100%. So, but that's, what we normally do with probabilities, all the possibilities add up to 100%. So discrete probability distribution, you got a variable, you got specific numerical values, a finite number of them that are discrete. For each of those, there's a probability associated, and then normal stuff applies with probabilities. All right, so that's what a discrete probability distribution is. Lots of words and stuff like that. So as I've pitched before, try to organize stuff, try to have a little glossary in your notes and stuff like that, so you can like look up what does discrete mean, what does quantitative mean, that kind of stuff. Otherwise, it gets harder to understand what's going on. Let's do some formulas. Yay, math those formulas. Okay, so we're going to do some formulas. So the mean and standard deviation, remember, this is a distribution of data, right? So if I had like 30 people take this quiz, a bunch of people are going to get 0 questions correct if they answer randomly. We know about 42% of them are going to get none of them correct. About 42% will get 1 correct. Many fewer, like 14%, will get 2 correct. And maybe some of them, but around 2%, will get all 3 out of 3 correct just by guessing. It's definitely a possibility, a 2% possibility, so it won't happen very often. So this is just a bunch of data. I have 30 people taking quizzes. There's a bunch of zeros, a bunch of ones, some twos, maybe a 3 or 2 or something like that. So that is a bunch of data, and we can talk about the distribution of data. And how do we talk about the distribution of data? Well, we talk about the center, we talk about the spread, and we talk about the shape. So center, we're going to be using the mean as a measure of center for these discrete probability distributions. And we have a wonderful formula for the mean, of course, and likewise for the spread, we're going to use standard deviation. And there's the formula for standard deviation. And we're going to do the mean by hand just to show you what that looks like. This little S symbol, as you've seen before, means to sum up, to add. So I'm adding all of the X times PX's together. So I'll show you what that looks like. I'll go up to my table here, and I'm going to say, I'm going to make a new column here, X times PX, right? So that's my new column. I guess I'll just extend the table a little bit so I can have spaces to write this. On the first one, the X is 0. Put that in red. The X is 0, and the PX is 42%. So 0 times 0.42. That's actually equal to 0, because 0 times anything is 0, but we're not going to go there quite yet. We have 1 is the next possible value for X, and that's also 42%. So 1 times 0.42. Next one is 2, and the probability of getting 2 correct is 0.14. 0.14. And the last one is 3 questions correct have a probability of 0.02. And then I basically add these all up. I do the multiplication as 0 times 0.42, 1 times 0.42, 2 times 0.14, and 3 times 0.02, and I add them all up. I just add all these together, and I get a total. And again, I'm going to use Desmos to help me do that. So right over here, the third calculation, I have 0. The probability of getting 0 questions correct is 42%. 1 was 42%. To get 2 answers correct is 14%. To get 3 answers correct is 2%. I add all those together, and I get 7.76. So 0.76 is the mean value of X. X measures the number of questions you get correct. So the mean number of questions you get correct is 0.76, like between 0 and 1 questions correct, which probably makes a little bit of sense because we know most of the people either got 0 or 1. 42% got 0, 42% got 1. So most of the people are getting between 0 and 1 correct anyway. And there's nothing below 0, of course. And you can get higher than 1. So you can get 2 answers correct. You can even possibly get 3 answers correct. So the mean, the average, is going to be a little bit higher than directly smack dab in the middle of 0 or 1. So 0.76 is what it ends up being. 0.76 ends up being the mean number of questions correct. So if you take the number of questions correct for everyone, you add them all up, you divide by how many there were, you get 0.76 correct answers on average, on the mean. So that's how you calculate the mean. Standard deviation is a much more complicated formula, as you might remember doing standard deviations. You have to find out how much the data deviates from the mean, and then you have to add those up and square them, and then you have to square root that. And it's a complicated formula. I'm not going to do it by hand, but I will show you how to do it using StatCrunch. So I'm going to jump over to StatCrunch. I've already typed in the data here, the probability distribution. So here's getting 0 questions correct. There's a 42% chance. And likewise, 1 is 42. I just typed in the table just to save time on the video. So we're going to calculate the mean and standard deviation for this probability distribution. So I'm going to go under stat, and there's a whole bunch of calculators. There's all the calculators here. There's no specific calculator for a discrete probability distribution. Discrete uniform is not what we want. We have to go all the way down to custom. So for a discrete probability distribution, we go down to custom and we say, where are the values of the variable? The values of the variable are 0, 1, 2, 3, which are in var1. And then the weights, which means the probabilities are right here for each of those x values. They're in var2. So weights, values of the variable and weights or probabilities, and I hit compute. And I can get 0 correct, I can get 1 correct, 2 correct, 3 correct. The mean is 0.76, which we just calculated by hand. Standard deviation is 0.76315,136. It's just a calculation. And so that's the standard deviation. That's how spread out the data is. I'll kind of give that a little bit more of a definitive meaning in a second. And we can even like do a probability calculation. Like, for example, the probability of exactly one correct answer is 42%, like what we just figured out before. So that's the discrete probability distribution calculator under stat calculator, and then custom gives you this one right here. Okay. And so I wrote down this number here, 0.7632, as the value of the standard deviation using this formula, but actually having StatCrunch use the formula for us. It's much better at doing those formulas than most people, just because it's a lot of tedious calculation and easy to make little mistakes. Much harder for computers to make those sorts of mistakes. So just to kind of remind you what the standard deviation thing tells us, the 0.76 number tells us the spread. So if you start from the middle, which is 0.76 questions correct, and you subtract 0.7632 or add 0.7632, that's called one standard deviation away from the mean. And we know from the empirical rule, from the 68, 95, 99.7% rule, that 68% of the data should lie between those two values. So 76 minus 76 is 0. 76 plus 76 is about 1.5. So I know about 68% of these people who take this 3-question quiz will get between 0 and 1.5 questions correct. So that's the spread out of the data. 2/3 of the data, 68% of the data, a little bit more than 2/3, is between 0 and 1.5. So that's what my standard deviation tells me right there. Okay, so that's a bit of stuff on the discrete probability distribution, which you won't see a lot of questions about because, again, we're going to be focusing more on the binomial probability distribution, which we're going to do right now. All right, binomial probability distribution. Sometimes it's called a binomial distribution. Some people just shorten it to say binomial distribution. They don't have the word probability in there because it's sort of implied, I guess. So what is a binomial probability distribution? Well, it's actually a special type of discrete probability distribution. The one we just did previously was a discrete probability distribution. The example I gave was there's 4 different values of x, and it's a probability for each of those. So the binomial distribution is a special type of one of those guys. The restriction or the big idea behind a binomial distribution is there are only 2 possible values for x. The prefix bi in English means 2, like a bicycle has 2 wheels and stuff like that, right? So a binomial distribution, there are only 2 possible values of x. So it's like in my quiz example, there's only one question there's only one quiz, right? There's only one quiz question, and for that one quiz question, you either get it right or wrong. There's only 2 possibilities, right? The probability, if there's 4 answers for each one, the probability getting it right is 1 out of 4, which is 25%, and the probability getting it wrong is 3 out of 4, which is 75%. There's only 2 possibilities, right or wrong, right? And so that's what we mean by a binomial distribution. Is it's a discrete probability distribution where there are only 2 possible values of x. The really kind of cool thing that math people really like to use about the binomial distribution is this thing right here. Because there are only 2 possibilities, we can actually use all the formulas for a binomial probability distribution, even if the x values are not quantitative. They're not even numbers, right? So we can do all of our basically discrete probability distribution stuff even when we don't have numbers for x. So classic examples are you have a yes, no question. So there's only 2 possibilities, binomial, 2 possibilities, yes, no. They don't have to be numbers, or maybe a win-lose. two possibilities. So we can use all these formulas even if we don't have quantitative values of our variable. We have to only have two possible choices though. So these are called categorical variables where, they're words, they're not numbers, right? Okay, so vocabulary check-in time. So important to know the vocabulary. So there's only two possible outcomes. Math people will always call one of the possible outcomes a success, right? So one of the possible values is success, and the other one is going to be considered a failure. So in the yes/no question, maybe yes would be considered a success, and no would be considered a failure. Or you could do the other way. You could, whichever way you want to do it, you could say no is a success and yes is a failure. You just have to declare which one you want to be. So they're going to call one of them always a success, and the other one always then becomes the failure, no matter what it is. You get to decide, or the problem that you're solving will decide for you. Okay. A little bit of nomenclature. Nomenclature means like the letters and symbols used in the math stuff. So we have the letters P and Q for a binomial distribution. P is always the probability of success, and Q is always the probability of failure. So in my example, let's suppose in my like one question quiz example, suppose success was getting it right. So if success equals getting the one question correct. In my example, like there's four possibilities, then the probability of a success would be 1 out of 4, or 25%. And the probability of failure, which is going to be represented by the letter Q, is 3 out of 4, because there are 3 wrong answers, and that's a 75%. You can write these as decimals if you prefer. It's up to you. Same thing. So we have P and Q, these letters that represent the probability of success and probability of failure. A little warning coming up here. I could not help, but at this point, kind of go over something. Many students start to notice that the letter P is used to mean lots of different things in statistics. So I'm going to go over kind of the main ones that we have seen so far, or that we will see soon in the chapters coming up. So in the very beginning, when chapter 1, we said P is going to be the size of a population. So P was the size of the population. Now we're seeing P is the probability of a success, right? Same P, right? Capital P is the probability that something occurs, the probability of X occurs or some event. Math people sometimes just abbreviate this with a capital P. They don't put the X inside. So again, P, in this case, capital P, is the probability that something occurs. Then they have this P with a little like thing, it's pronounced P hat. It's like a little caret up there. P hat, you'll see soon, is the proportion that has a specified characteristic, oftentimes called the sample proportion. Then we have P with a line over it, pronounced P bar, and that's the mean proportion. And then you have a P value, which is the probability that an event occurs by chance. I'm just showing this to show you that the letter P is used in lots of different places to mean different things. And one of the big hurdles of statistics is that there's all kinds of different new vocabulary and letters and used, and you can see that even letters are reused to mean multiple different things to add to the confusion. When you see the letter P, it can mean one of 6 things, or maybe other things depending on the context. Keeping track of all that, being organized, is really going to help, right? You're going to thank yourself if you have a place in your notebook where you keep track of all of the different letters being used, all the different words. What does discrete mean? What does quantitative mean? All that kind of stuff like that. And the formulas, like you're taking statistics and you see a word problem. It sounds like all the other word problems you're doing. The formulas all are kind of similar. Which formula do I use for which type of word problem? That is the hardest part about statistics. Just kind of keeping track of everything. So if you can keep organized and keep a glossary and have everything written down, you're going to thank yourself quite a bit especially as we get further and further in the course and we get more and more stuff and more formulas. Boy, you'll be much happier if you have good notes that are organized and you could track stuff down. Oh, that's what they want me to do. And then you can just do it and get the right answer. All right, enough of my little lecture here about being organized, taking notes. Let's go into some examples of a binomial probability distribution and the formulas, of course, that will give you those answers. All right, so we have the mean standard deviation, and we also have a formula for calculating the probability of n particular outcomes. Okay, so formulas for mean and standard deviation are here and here. And then we have probability of R successes. I'll show you an example of that just in a moment. You notice that it uses stuff we learned in chapter 4, which is a number of combinations. You're choosing R things out of a size of set n, number of combinations, times p to the r times the q to the n minus r. That's a formula for the probability number of successes. It's kind of a, lengthy formula. So we're going to try to use StatCrunch to do that one because it is a bunch of work. You could do it by hand again. It's not something that's not undoable. It just takes a bit of work. The NCR thing you've done many times before in chapter 4, P to the R, P is the probability of a success. R is that number there. So you have, 0.25 to some power. And then Q is the probability of failure, and you get it to a different power. It's just a calculation. All right, so let's do an example so you can kind of see what I'm talking about. So I have here a game of blackjack, and it's okay if you've never played it before, it doesn't matter. In the game of blackjack, we have a theoretical probability of being dealt 2 cards that add to either 20 or 21 is approximately 15%. So we can do the calculation, but we're not going to do that. We're just going to take the information from this problem. If you have not played blackjack before, a 20 or 21 are the 2 best starting hands. So the probability of getting dealt one of the 2 best starting hands is around 15%. And suppose we have 50 people who play a game of blackjack. So our sample size, our population is 50 people. They're all playing a game of blackjack. And for people who have played blackjack before, who are familiar with the game, if 50 people were sitting next to each other, the probabilities change a little bit. We're going to say that the results are all independent. Maybe they're sitting at 50 different tables or whatever, right? So we're just going to say for the ease of explanation of how this binomial distribution works, that someone getting a 20 over there doesn't influence someone getting a 20 over there, right? They're independent events. All right, so we're going to be talking about the mean number of people who get 20 or 21. So again, we have 50 people who play the game, right? And we know that getting a 20 or 21 is about a 15% chance, right? And we want to find the mean and the standard deviation and the probability and stuff like that. All right, so how do we find the mean? Well, our formula here for mean is n times p. So this little symbol here, which is pronounced mu, math people use that to stand for mean. It's n, which is the number of people, 50, times p. This p is the probability of success. Remember, we want to know if people get a 20 or 21. So we're going to consider success getting a 20 or 21. And we know the probability of success is 15%. So I'm going to multiply 50 times 0.15. And let's see if I did it on Desmos already. I think I did. Yeah, here it is. 50 times 0.15 is 7.5. So 7.5 is going to be the mean. So we're trying to find out the mean number of people who get 20 or 21. The mean number of people who get 20 or 21 is 7.5, which means if we get 50 people playing a game of blackjack, we would assume, most often 7 or 8 people get either 20 or 21, right? So between 7 and 8 people is the majority, the center, the most common number of people who get 20 or 21, these good starting hands. I just put the answers over here just to keep me on track and make sure I don't mess up in the live video. So also, if you want to work ahead, which is always a great thing, always recommended, you can try to find the standard deviation of 20 or 21. Of course, you can just pause the video if you need a little bit of time. And I have the answers right over here, so you can double check to make sure that you got it right, or you can just listen to the video before, after trying it and kind of see how I do it. So you can learn the steps. And if you did try it before, you can learn where you got stuck perhaps, and you can finish it up, or that you get confirmation that you did get all the steps correct. All right, so how do we find the standard deviation? Standard deviation, the symbol used for standard deviation is this little sigma symbol there, the circle with a hat on top, and that is the square root of n times p times q. This one right here, n times p times q, right up there. That's supposed to be an arrow. It looks like a mess. Okay, it is a mess, but it's still supposed to be an arrow. So n, which is the number playing the game, 50. P, which is the symbol they use for the probability of a success. And Q, which is they use the symbol for the probability of a failure. If 15% is a success, and we know that the probabilities have to add to 100%, if 15% is a success, then the failure must be the 85%, right? Because you have to get 100% altogether. All right, so we know what Q is. It's just the remainder from 100%. So I'm going to multiply times 0.75. So that's the formula for calculating the standard deviation of 50 people getting 20 or 21. And of course, I did do that on Desmos. I checked. It's right here. Square root of 50 times 15, 0.15 times 0.85. That's n times p times q is about 2.5248, some number there. I think I rounded it just to 2.5 just to make it easier to talk about the calculations. Yeah, there's 2.5. So that's our standard deviation. So we got 7.5. So we'd expect around 7 or 8 people to get dealt 20 or 21 out of these 30 people. 30 people playing. Scratch that. 50 people playing. 50 people playing. We expect 7 or 8 of them to be dealt this great hand. And 2.5, that is the deviation. That's the spread. We'll talk about that a little bit more. But remember, the first thing you should be thinking about spread is I add it and subtract it from the mean. So if I take 7.5 and I add 2.5, I'm adding this number, or I'm subtracting that number. I don't know how to do subtraction. Minus 2.5. I'll do it that way. Hopefully it doesn't look too confusing, right? So if I add or subtract 2.5, so I'll do 2.5 this way and 2.5 this way. This gives me 7.5 plus 2.5 is 10, and 7.5 minus 2.5 is 5. So between 5 and 10. So what does that mean? We would expect that 68% of the people, the plus or minus 1 standard deviation is always 68%, 68, 95, 99.7. Remember that whole empirical rule thing? So when you're talking about standard deviation and you want to make sense of it, first thing to do is add and subtract the standard deviation from the mean. So 7.5 plus 2.5 is 10. 7.5 minus 2.5 is 5. So we would expect 68% of these 50 people, most of the people, to get between 5 and 10 of these great starting hands, right? Getting the best 2 starting hands between 5 and 10 people, there would be about 2/3, about 68% of our 50 people, most of our people would get between 5 or most of the time. I think I said that wrong. Okay, most of the time, 68% of the time, we would have between 5 and 10 of these great starting hands. I think I said it backwards before. So let me say it one more time just to clarify. I'm taking the 2.5 and adding and subtracting it, and I get 5 and 10, right? So 68% of the time, of these 50 people, would imagine that between 5 and 10 of them got these 1 or 2 special starting hands, 20 or 21. Okay, sorry for the mix up there. I think I said it backwards at first. All right, so let's talk about question C here, the probability that 10 people get 20 or 21. So that would be the probability of 10 successes. And that's our formula right here. The probability of our successes, the probability of 10 successes. So we still have 50 people. So we would have, for this one down here, we have the number of combinations from 50 people. We want 10 successes. And then we get P, which is our 0.15 to the R. We want 10 people getting a success. So to the 10, that's the same as this number here. And then we would do the failure. Failure is 75, not 57. Oops, where's my eraser? There we go. All right, 75. And then we would do N minus R, which would be 50 minus 10. I guess I could put 40 up there, but I'll put 50 minus 10 so you can see how the formula works. So we could do this calculation and hunky-dory, but again, let's use StatCrunch to do this for us. Okay, here we go. So I'm going to go over to StatCrunch. I don't need this stuff up here, but I don't have to worry about it. I can leave it there for now. It's not going to change anything. I'm going to go to Stat Calculator, and I have an alphabetical list of all my different calculators. I'm not going to custom anymore. I'm going to go to binomial because it has a list for the binomial probability distribution right here. So I go to my binomial distribution. It's towards the top because of the alphabetical thing. And for a binomial, it brings me up a calculator. I have to specify the number of outcomes, the number of people who play the game of blackjack. We said there were 50 people who played. My computer will update in a second. And then we need P. This P is the probability of success. So we said it's 50 here. We said the probability of success was 15%. You know, we can double check that if you want by going back to the lecture notes. 50 people play, probability of success is 15%. All I did was I just typed that into a StatCrunch, and we'll change this in a minute. I'll just press compute. And so here is the distribution of the data. And you can see right in the middle, 7.5 is where sort of the most common is, so the mean that we're talking about. We are looking for, in our particular example, the probability that 10 people are successful. 10 people get a 20 or 21. So let me go here, probability that X equals 10. So this is probability that 10 people are successful in getting a 20 or 21, and I hit compute, and I get 0.0889, so 8.9% or 9%, depending on where you round it. You'll see that it shows here in red, that's the 10, so you can visually see that this is the number of people who get it correct, and 10 people is right around that 9% range. What did I put as my answer here? I guess I rounded it to one decimal place, so 8.9%, or 9% if you round it to a whole percentage, and get of the time 10 people get 20 or 21. So that's the percentage of the time that 10 people get either a 20 or 21. 8.9%. 9% of the time 10 people will get that. What about my next question over here, which is what is the probability that at least 10 people get 20 or 21? Well, at least, you may have remember playing this game before. At least means that number or larger. So at least 10 people is 10, 11, 12, 13, that kind of stuff like that. So I'll go back to my StatCrunch, and it's saying instead of saying the probability that X equals 10, I'll say the probability that X is greater than or equal to 10, right? And that seems to be about 0.20, 20%, or 0.21, something like that. So that would be, okay, this is this is the probability of getting of these 50 people, of 10, at least 10 of them getting the best earning hand, and it's around 21%, 20.8, 20.9%, something like that. Okay, what do I have? Yeah, 20.9%. There we go. All right, so that's using the StatCrunch calculator to do this kind of problems. And then I did want to just come back to the empirical rule fast, because a lot of people have a hard time explaining standard deviation or how to use it or what it means. And I just want to cycle back to the empirical rule, which is the 68, 95, 99% rule. Those numbers come up a lot, especially when we're trying to talk about measures of a distribution of data. This is also called the empirical rule. It's also called the range rule of thumb. A lot of different words mean the same thing. So just kind of be on the lookout that they're going to call the same thing using a different set of words depending on who says it. People say it in different ways. That's just the way things go with communication. So you have to kind of be aware of the synonyms of what means the same and stuff like that. So we're going to determine which numbers of people getting 20 or 21 is significantly high. Significantly high would be +2 standard deviations. So significantly high and significantly low are plus or minus 2 standard deviations. That's the 95% rule, right? So if you're not within the 95% of the data, if you're not within 2 standard deviations, then it means you're really high or really low. You're like significantly high or significantly low. So that's what significantly high means. it means you're beyond the 95%. You're plus 2 standard deviations away. So once again, we take our mean. Our mean is 7.5. And we add 2 standard deviations. So a standard deviation, by the way, is 2.5. You remember that? So we're doing 2 plus 2 of our standard deviations. And what do we get? 7.5. Okay, I have to do I have to do the multiplication first because math, right? So I have to multiply 2 times 2.5. So that is 5. 2 times 2.5 is 5. If I take 7.5 plus 5, I get 12.5. So if you're above 12.5, you're significantly high. So if 13 people got 20 or 21, or more than 13 or more people got 20 or 21, we would consider that a significantly high number of people getting 20 or 21, and might be a little suspicious if you're, security or whatever at the blackjack place. You're like, wow, 13 people got 20 or 21. Something funny may be going on. We might need to investigate it. Certainly, if it happens again, we're really concerned that the game is not what we think it is, right? Because it's significantly higher than 95% of these distributions of 50 people playing the game. All right, so just a little recap on the 68, 95, 99.7% rule. One more example about the binomial distribution, and then 2 quick examples on the other 2 types of probability distributions, and that will be the end of the video. So we're actually nearing the end of it, even though it seems like we still have a lot to go. The binomial distribution is the one that's the most important one, right? So again, make sure you know the binomial probability distribution. It is the one that is used quite a bit, and it's kind of the main one of the probability distributions. The other ones come up, and well, I'll show you when they come up. So I'll show you when they come up. So I mean, I gave you an example of the discrete one, and that was for like you have like a bunch of choices. You can also use the discrete probability distribution to like calculate your grade in the class when like quizzes are worth 10% and homework's worth 15%, stuff like that. It's the same thing right there. Anyway, anywho, let's follow the script here and not segue into other stuff. Okay, so question or example number 2 I have right here. According to the 2023 US Census Bureau, 92% of Americans have some form of health care insurance, public or private. Suppose we have a simple random sample of 1,000 Americans. We ask them if they have some form of health care insurance. Now we know that 92%, at least according to the US Census Bureau, 92% of Americans do have some form of health care insurance. So when we ask 1,000 people, we'd expect most of them to say yes, right? We'd expect around 92% of them to say yes. So our question is, what is the probability that fewer than 920 of those surveyed have some form of health care insurance? So when you're looking at a problem like this, you need to spot the idea that there's either a yes, I do have some form of health insurance, or no, I don't have some form of healthcare insurance. Yes or no, 2 possible choices, binomial, right? So when you're reading a problem like this, kind of saying, oh, what are the possibilities? Oh, it's yes or no. Oh, that's a binomial distribution. So I immediately want to go to my binomial calculator. I know that there are 1,000 people who were asked, and that we know that the probability of successfully having healthcare insurance is 92%. So go over to my StatCrunch. I'm going to use the same calculator. I mean, I can open a new calculator, but it's the same thing, stat, calculator, binomial, right? It's the same calculator. So I'll just use the old one and just change the numbers, right? So instead of 50 people, we have 1,000 people. Okay, my computer's going to glitch for a sec. And then for the 1,000 people, we need the probability of success, which I believe we said was 92% or 90. I have to look it up again. Bad short-term memory. 92%. 92. So I kind of did remember 92%. Okay, so I go over here, and the probability of success is 92, and I'm looking for the probability that fewer than 920, so less than 920. Let me double check that that's correct. I'll just reread the word problem. What is the probability that fewer than 920? So fewer means definitely less than 920. It doesn't include 920. So fewer than 920 is less than 920. Hit compute. So here's the 920, which of course is what we'd expect to have happen, but fewer than 920 are all of these values here. These are all the ones, the surveys that we could have had. We could have had 910 people say that they have healthcare insurance. These are all the ones that are fewer than 920. And what is the probability that the number is less than 920? It's around 47%, 0.47. So what is the probability that fewer than 920? It's 47%. So for these questions, you don't actually have to do a lot of analysis. You don't have to do all the calculations for the mean and think about the empirical rule. For a lot of the homework questions, it'll just say something like number 2, and you open up the binomial calculator and you say, oh, there's 1,000 people, success is 92%. Boom, what is the probability that we have fewer than 920? It's 47%. So just like that. All right, so that was an explanation, kind of a long, detailed explanation about the binomial probability distribution, a couple of examples of how it works, formulas, calculating some by hand. StatCrunch doesn't really do the mean and standard deviation calculations in the calculator. You can see in the calculator, it doesn't actually tell you the mean and standard deviation. So if you have to calculate the mean and standard deviation, the formulas aren't complicated. Mean was just n times p. That's this formula right here. And then the standard deviation was the square root of n times p times q. So you can do those very easily by hand. If you really want to use technology, I would recommend using something like Wolfram Alpha. Wolfram Alpha is a great knowledge engine, and it's kind of like Google, but Google for like math and science and stuff like that. So you can just type in anything you want. So for example, I could type in what is the mean of a binomial distribution with n equals 50 and p equals 0.15, and it would tell me that the mean is 7.5 and standard deviation is 2.5, right? So you could just type in whatever you want and it'll tell you the answers for those. 7.5 and 2.5, if you recall, were the mean and standard deviation that we figured out in this problem right here. 7.5 was the mean and 2.5 was the standard deviation, right? So it'll do it on Wolfram Alpha if you don't want to do the calculation by hand. But StatCrunch doesn't really do those things. I guess they assume that it's easy to do by hand. So why bother? It's a strange omission in StatCrunch, but it is what it is. Okay, last page. Let's go to last page. We're done with binomial distribution. You will, of course, ask me questions if you want to know more about binomial distribution. Let's talk about the last 2 types of probability distributions. One is called the geometric probability distribution. So we have to know what a geometric probability distribution is used for and the formula for it. And then right down below, I have the Poisson probability distribution, what it's used for, and a formula. Not used frequently as much as the binomial distribution, but we are going to learn them, and you will definitely have questions on those. Okay, so what is a geometric probability distribution, you ask? Well, I'm glad you asked, because this is the part of the lecture where I tell you. A geometric probability distribution is similar to a binomial probability distribution, but we won't necessarily know the number n of observations or if n is ongoing. So we still need to assume that observations are independent. We have a big formula here, and the formula is used to find the probability that the first success will occur after our observations. What? Okay, so let me give you an example so you can see what I'm talking about. So here's my example right here. Number 1, you're rolling a 6-sided die, normal 6-sided die, and you keep rolling it until you get a 3. That could happen right away, or it could happen like it could take you, if you're unlucky, a lot of rolls, but you're going to keep rolling it until you get a 3. So the number of times we roll the die, we don't know, right? It's ongoing until we get a 3. So we don't know the number of times that we're going to do the experiment, the observation. Each of those rolls is independent, right? If I don't roll a 3, if I get a 5 or something, the 5 doesn't go away. Like I can still get another 5, or the numbers are repeatable. One die roll doesn't change the next die roll, so they're independent. And I'm going to keep rolling this die until I get a 3. So I'm going to try to find the probability that my first 3, the first time I roll a 3, occurs on the 5th roll. So that's what we mean by the probability that the first success, the first 3 I get, will occur after 5 observation, after 5 rolls. So I want to find out the probability that I get a 3 on the 5th roll. So I'm going to go to StatCrunch, and I'm going to go to my calculator. So this is a geometric probability distribution. So I'm going to go over to my calculators, and I'm going to look at geometric. There it is, geometric probability distribution. We'll do a number of failures, I guess, with this one here. So our probability of success, well, we're rolling a die. Let's go back over here. We're rolling a die, and we're trying to get a 3. So the probability of getting a 3 is the number of ways to get a success divided by the total number of ways, right? Just like you did in probabilities in chapter 4. So in our case, there's only 1 3 out of 6. So our probability of getting a 3 is 1 out of 6. There's only 1 3. There's 6 sides of the die. So our probability is 1 out of 6. And we're trying to get on the 5th roll. So my probability here, I'll just write 1 out of 6. I won't even do it as a decimal. It doesn't care. Well, my computer is doing this like updating thing all the time. So patience. Okay, there we go. 1 out of 6. Nope. One more try. 1 out of 6. So my probability of success is 1 out of 6. And then I want the probability of 5. So I want the probability that occurs on the 5th roll. So there's a 1 in 6 chance I get a 3. I'm looking for the probability that it occurs. Come back. I don't know what I just did. Let me go to my hidden results. I want the geometric calculator. So probability of the 5th one being a success is 0.0669. And you can see the little red line here is at 5. 1, 2, 3, 4, 5, right? This is probability of, I guess, 0, 1, 2, 3, 4, 5. I should have started with 0, but this is the probability that it would take 5 observations in order for me to get my first 3. So let's double check that. So 8% here. So on the 5th roll, so maybe I made a mistake. Let me pause and make sure that this is correct. So I can make sure that you are watching something that is not full of errors. So 1 sec, please. Okay, so I did find out that I messed up, and I don't know if you saw me pause before, but let's go back to StatCrunch. Thank you. This is the geometric calculator for the number of failures. So we're trying to find out the first time a failure occurs. This is not the option I want. So I'm going to close this. I was like trying to remember, and I remembered it wrong. I apologize. So I'm going to go to Stat, Calculator, Geometric, and we're going to do trials. We're going to know how many trials until we get a success, right? So I clicked on the wrong thing because I remembered it backwards. So we're going to click on the bottom one, the trials for our homework. Make sure you do that one. And once again, we're going to do the probability of success is 1/6. 1 3 out of 6 possible sides. We want the probability that that the success occurs on the 5th roll. So we'll do it that way. And there's the 8% that I had computed before. So 0.08 is 8%. And now there's 1, 2, 3, 4. 0 didn't even make sense before. I was trying to figure out why there's 0 there. It's because you can have 0 failures. But anyway, do the trials, number of trials, and it'll be way easier. Okay, so 1/6 possibility or probability of success, 5 again, I hit escape and it goes away. So let me go back to here. Number of trials, number of trials. Here we go, number of trials. So it's 8%. So like that's the answer for the probability that we get our first 3 on the 5th roll. Okay. Thanks for your patience. Probability that your first 3 is on the 6th roll, that's the 8% that we just saw on StatCrunch. Let me do it in green so it looks a little bit different for color-sided folks. Okay. What is the probability your first 3 occurs by the 5th roll? And I did parts A and B purposefully because when you're reading math problems, a lot of times our eyes focus on the numbers, right? And we don't focus so much on the little bitty words, right? Like the prepositions or things that connect things together, right? So if you look really carefully between A and B, they look almost identical, but the key difference is on or by. All right. So, whoops, that looked a little messy. But that one, well, there's 2 letters, right? That one little word, that one little 2-letter word, if you say on the 5th roll, that means it has to be exactly on the 5th roll. By the 5th roll means you can get your 3 on the 1st roll, 2nd roll, 3rd roll, 4th. You can get it on any of the rolls, but it has to be by the 5th roll. So how do we make StatCrunch do the by the 5th? Well, instead of saying equal to 5, we'd say less than or equal to 5. Less than or equal to 5 would be by the 5th roll because you can have it on the 5th or the 4th or the 3rd, something like that. So then we'll compute that. And it's about 0.598. If I round this, it's about 0.60, about 60% of the time. So that should be my answer for that question. Yeah, 60% right here, 60%. So 60% of the time, we would imagine getting a 3 by the 5th roll. So that is an example of the geometric probability distribution. It's used to find the probability that the first success will occur after our observations. Last one is the Poisson probability distribution. Poisson probability distribution, another one of these distributions. What are the characteristics of a Poisson probability distribution? Well, it's also similar to a binomial probability distribution. It's used when the n is very large and the p, the probability of success, is small. So we have to have, generally, to get accurate results, we need a large number of observations and the probability of success, the p, being small. And don't get too wrapped up into what very large and small is. If you want to do some more advanced statistics, there's formulas for calculating how large is large enough and how small is small enough. We're just going to do it sort of to get the idea in our first stat course. So those are great questions. How large is very large, but we're not really going to answer them at this level of statistics. A little more complicated, a little bit above our pay grade at this moment. Okay. Once again, we're still assuming that everything's independent. So one success doesn't change another possible success in the future. And what's interesting about a Poisson probability distribution is that successes occur at an average rate, a fixed average rate. So if you're not sure what that means, let me show you an example. There's a crazy formula for the probability that you get R successes in a given time. And that's this formula right here. And that tells us that the Poisson probability formula finds the probability that our successes will occur in a given time. That crazy formula, I mean, you can do it by hand. It's not that complicated, but of course, we can use StatCrunch and do it for us. So we'll be using StatCrunch for this one as well. So here's my example to help explain what the average rate of time is and how we use the Poisson probability distribution. So this example right here. So suppose over the past 365 days, a vacuum factory makes 10,000 vacuums. What is the probability that the factory will make 30 vacuums today? And I'll also ask the second follow-up question, at least 30 vacuums today. Okay, so over the past 365 days, they have made 10,000 vacuums. So 10,000 vacuums over, I'll assume that you know the word vacuum, over 365 days. So to write that as a rate, we have to write it as a rate. Rate. We're going to do the 10,000. I'll spell it out this time. Vacuums over 365 days. That's going to be my rate. And when I divide this out, I'm going to get the number of vacuums per day. All right. It's because I divide it out over the 365 days. I'll find out the VACUUM, I think, the number of vacuums per day. So it's 10,000 divided by 365. Let me do that real quick in Desmos. So I don't think I did that before. Yeah, here we go. 10,000. Okay. Again, one little pause for my computer to wake up. 10,000 over 365. All right, so that's a 28.397. I guess I'll just copy all those decimal places. I mean, I don't want to copy all those decimal places. Let me just copy a few of them. There we go. 27.397. I'll just copy that. Oh, it won't let me do that. All right, I'll just copy. Okay. I have a failure here to use technology, but old people, that's just normally what we do. So I'll hit Control C instead of trying to use the pull down menu. So I've copied 27.397 to my clipboard. That is the average number of vacuums per day. Okay. So now I'm supposed to write it down and I instantly forget what the number is. 27.397. 27.397. 27.397. So that would be the average number of vacuums per day that this particular factory makes. Okay, so now we know the average rate, right? It's about 27-ish vacuums per day. And we want to find out what is the probability that 30 vacuums will be made today. So today is one day, right? So we're not talking about 2 days. We're talking about today, which is one day, right? So what is the probability that the factory will make 30 vacuums in the one day that is called today? So that is the question of what is the probability that our successes will occur in a given time t. The probability that 30 successes will happen in a given time of one day. So that's what I mean by the probability distribution formula finds the probability that you'll have R successes in a given particular time frame. What's the probability that we have 30 vacuums made in one day? And we do have to know the average rate. The average rate we computed was 27.397 vacuums per day. Now we have a great big formula that we can do by hand, but we're going to use StatCrunch to do it for us. So back to StatCrunch, hide this guy, go to my stat calculators, and go down to where the P's are. Poisson calculator right here. There's my Poisson calculator. I have to know the average. The mean is the average. So let's see if I successfully, yeah, there it is. 27.397 was the average. And we're trying to find the probability that we have. I typed this up myself and I forgot it. 30 vacuums today. So exactly 30. So the probability that X is equal to 30. Compute. So there's the 30, and there's the probability that today, in one day, you're going to make, the factory will make 30 vacuums. It's about 6%, 6.4%, something like that. Let's see. Yeah, 6.4% right there. And then my follow-up question is, what's the probability that they'll make at least 30 vacuums today? Well, we've played this game before, right? The difference between Making 30 vacuums a day and at least 30 vacuums a day is the inequality sign, the equal sign versus a greater than or less than sign. So at least 30 vacuums could be 30 or 31 or 32. At least 30 means it could be 30 or more. So I'll go back to my StatCrunch guy, and instead of saying exactly equal to 30, I'll say 30 or more by doing this symbol right here, greater than or equal to 30. And I think it did it automatically. Yeah, 33% is greater than or equal to 30. And you can see all the red now here. This is, they can make 30 vacuums or 31 vacuums, or they can make any number of vacuums. Of course, it's less likely they make a lot more than 30 because the average is only 27. But these are all the different possibilities, and you add them all up and you get about 33.4%. Let's see if I have that there. Yeah, there we go. Okay. So that's a Poisson probability distribution, or some people just say Poisson distribution. It's the probability that you have R successes in a given time frame, and you have to know the average rate of time in order to do the Poisson calculation. Now, one final thing before I end the video. A lot of people have a hard time with the time thing. And I'll give you an example. Suppose I changed this problem. Suppose I said, instead of over the past 365 days, suppose I got rid of this and I said over the past year. I think a lot of students, if they haven't practiced Poisson distributions before, would be confused. So focus on the question. The question talks about today. Today is one day. Today is not 3 days. Today is not a year. So the day is 1 year. So we're trying to use the Poisson formula to find the given time one day. That means your average has to be in days. So this means the average, average, if I can spell average, I'm not sure. Average must be in days. So you would still get the same average, but there's no 365 that it looks like in this problem, right? You'd have to know to switch a year into 365 days so that you would have the correct day to match up with the day here. So your time measurements have to match. If you're looking for the number of vacuums in a day, then your rate has to be in days, even if they gave you the problem in years to be like tricky and sneaky. You need to be aware and switch it to days so everything matches up. So that's kind of my warning to you, is sometimes they will try to get sneaky, and they'll give like the 10,000 vacuums in a year, and you'll have to know to make that 10,000 vacuums in 365 to do the calculation to find the correct average. Okay, I just wanted to point that out. That is the end of our learning objectives for 5.1 through 5.3. And just to reiterate, just to recall, we have 4 different types of probability distributions: the discrete probability distribution, the binomial probability distribution, the geometric probability distribution, and the Poisson probability distribution. Each of those has formulas on how to calculate stuff. Each of those is used for different types of problems. So you have to know the type of problem to use each of those types of things. Binomial is the one that comes up most frequently, but as you saw, other ones will come up sporadically as well. Okay, hopefully this video was useful, helpful. Hopefully you will reach out if you have other questions or want some more help. Or if you just want some what if scenarios, like what if I did this, or what if this was the problem, what would I do? Happy to help in any way. Just let me know, and I hope you have an enjoyable day.